This con
So welcome everyone to another OCP session. This will be like number 70, and this one like a special format. And basically, thanks to Lasse, which came up with this creative idea to make a PTM night, and probably he's gonna break. Definitely, he already broke the record of attendees in an event. So we have four and a half presenters here, considering myself half. Uh, so we will go through various topics and start basically with Lasse's presentation, which in the second part of it, we'll talk a little bit about applications, and then we'll go with Kevin, and I think next will be like Wojtek and Brian. So let's start again, similar format that as usual we do. We present, like basically we give the bio for Lasse. So Lasse Johnson, I don't know why he has also this extremely amazing title, table tennis player at TimeBeat.app. So Lasse has been working with networks and systems for over 20 years and has for the last half decade been working with high accuracy clock synchronization. He is the co-founder of TimeBeat.app and the inventor of PTP plus squared mesh distribution system. Lasse is currently working on new software and hardware, including OCP Tab, Timecard, and the Timecard Mini to improve clock synchronization performance for all. And he also puts the Timecard today address that you can go see basically the latest and the greatest. So Lasse is also helping with OCP Tap on the communication. And yeah, Lasse, you officially broke the record of attendees. So well done. So with no further ado, Lasse, maybe you can start with your presentation.
Yeah, let me try. I cannot currently share that.
I made you a presenter. So.
Then I pressed the wrong button. I left and hey, here we go. Let's see. Okay, can you see this?
Yes.
I make it big. So you can see it full screen.
Yes.
Amazing. Okay, so yeah, I think PTM is quite interesting. And before we, hear from the other speakers who are quite frankly much more knowledgeable about it than I am, I thought it would be just useful to place it in context, okay? Because then everyone is understanding the technology at least. So let's have a quick look, okay? Um, here we go. So if we have a couple of computers, okay, as you do, and this can be a clock and something that's getting the time from a clock, or it can be, in the case of mesh distribution systems like PTP squared, it can be two computers sharing time with each other. Okay, we can achieve incredible accuracy between the NICs. Okay, and so suppose you have two NICs and they are connected with some fiber technology, some SFPs. Okay, they can be 100 kilometers apart, and they can achieve synchronization down to a couple of nanoseconds. Okay, and you can see an example of that below. So this is from this happens to be TimeBeat, but it could be PTP4L. Okay, so we have lucky packet filtering. So actually, we only stare according to the blue dots, and we filter out the red dots, and you can see them shown here on the right. Okay, and you can see we are literally down to the the theoretical limit when both NICs have a resolution of 1 nanosecond. Okay, so it's a plus minus 2 nanoseconds. But then there's the other, and by the way, here we use the Intel i225. Okay, and this is actually one of the NICs that have PGM capability, but okay, here is not used. But then we have the other half of the story, okay, which is the last 3 centimeters, okay, that we want to synchronize across the PCIe bus between the PHC, okay. PHC stands for PGP hardware clock, okay, and it's essentially just to explain a free running counter on the NIC. Typically it's like a 25 megahertz crystal, which is then increased with PLL to 125 megahertz. But it has a free running counter, I guess is the point. And in the CPU, okay, you have another free running counter. And so timekeeping is really all about deciding how many ticks of this counter, which is typically generated by a crystal, to get, for instance, a unit of time. Could be 1 second. And this varies with lots of things. For quartz crystals, if all of a sudden the NIC gets to be a bit hot, then the ticks, the frequency of the ticks will increase, and if it gets cold, it's the other way around. And there's some interesting graphs for how that works. But the problem we have between the PHC and the CPU is that we don't know the latency characteristics. Okay, so we cannot know how long time does it take when we ask the PHC to tell us what time it has. We cannot know exactly what is the time it takes for that message to get to the PHC and what is the time it takes for that message to get back. And then you have additional complexities such as when the CPU changes P state, okay? And this is some modern CPUs, they can change speed, okay, to save power. And and so essentially they run, so if you have a CPU that can run at a couple of gigahertz, it doesn't necessarily run at a couple of gigahertz all the time. Sometimes it throttles down to save power. And as these transitions happen, this can impact the counter in the CPU. It doesn't always happen. It works differently in different CPUs, but sometimes we see examples of a change in P state literally causing a static offset to be inserted between the time the PHC has and the time the CPU has. And this is quite interesting. So if you're interested in high accuracy clock sync and you have some servers in a data center, okay, for those that need accurate time, you should typically nail the CPU up to its highest setting so that it never changes P state. Okay, and then we can do some improvements in the accuracy when we measure the offset between the CPU and the PHC by doing some filtering, and different clients they have different strategies for this. But this is expensive in computational terms, and of course there's a PHC per NIC. So if you're synchronizing with many NICs inside the same server, okay, this can become expensive. Okay, so how is it actually done? So here we look at, later I'm hoping Kevin will explain how it works with the PGM, but I want to explain how do we synchronize the CPU with the PHC without the benefit of PGM. Okay, and okay, here I'm just let's say briefly explaining how the Linux PGP sysoffset extended IOCTL works, and actually I didn't look it up for the purpose of making the slide, so it's sort of from memory. I haven't looked at this in a while, but essentially the strategy is that, as you can see out there on the right, that you capture 3 timestamps. Okay, so first you capture a timestamp on the CPU, and then immediately after, okay, in a tight block of code, you then ask the PHC what time does it have, and then you ask immediately after you get the response to that, you ask the CPU again what time does it have, and then you make the frequently fairly terrible assumption that the time of the CPU at the PHC timestamp you got was right in between the 2 timestamps that you captured from the CPU. Okay, so you can sort of see how that makes sense. That you would assume that okay, roughly at this time in sort of in the linear progression of time at the CPU, was it the same as T2? But because when we ask for a timestamp, sometimes it can take a long time to get the message from the CPU to the NIC, and sometimes it can take a long time for it to get back. Okay, this is not always a great assumption. And so one way of one way of filtering this, one way of optimizing this process, okay, is that instead of doing this process one time, and we obviously have to do it typically many times a second because the 2 clocks drift in relation to each other. We do it a bunch of times, and then we assume that the best sample is the one where we have the shortest duration between T1A and T1B. Okay, and again, it does not always work like that. Okay, and then we can let's say if we want to see essentially this problem, okay, we can build this type of lab setup, okay, and if you have some time, let's say here, maybe this gets synchronized from pulse per second or from PTP, okay, you then in turn use this to synchronize the CPU, and then the time and the second NIC, okay, you synchronize from the CPU because the reality is that the 2 NICs cannot speak directly with each other, okay, there's no, let's say, standard API for doing that at least. So if we do this test, then you compare pulse per second output. So on network cards like the NVIDIA Mellanox ConnectX cards, which are very high quality, you have PPS ports, and even on other cards, Intel makes some that have also SMA ports for PPS, and so you can connect essentially your cards to an oscilloscope, or what we sometimes humorously call a spectroscope, but an oscilloscope, and then you can see the phase offset. Okay, and the reality is it does not work very well. It's not uncommon that in fact the phase offset between the 2 NICs is hundreds of nanoseconds. Okay, and this is even though you believe that you synchronize accurately at P1 and P2 because you see quite a narrow distribution. So you see a narrow distribution of offsets. Okay, so I guess the point is that the numbers you see when you run something like PHC to sys, okay, they are not actually true. Okay, and you cannot. It's very difficult really to understand how wrong they are. Okay, and so this has to be compensated for somehow, right? So you can see here is an example from an OCP server, okay, where you have in the bottom here is a time card, and at the top is a ConnectX-6 card, okay? And because without PTM, the strategy of synchronizing via the CPU doesn't work very well, you have to attach sort of cables between line cards, and this is not always ideal. Okay, and here you can see the same thing on Intel. And that's it. With this in mind, Ahmad can now talk a little bit about what are the applications if you do manage to get high accuracy synchronization on the CPU.
Sure. Yeah, thank you, Lasse. So I'm touching on some hypothetical, let's say, applications because again, the technology is new and developers are barely getting their hands on the technology. But I mean, overall, it should be pretty simple to understand that you want to have basically synchronization between two machines. Let's say all this goodness that we got from like the telecom world, telco world, adopting PTP over 15 years ago or more, has been based on what their applications are, and their applications are mainly you get the synchronization to, and again, last I called it a PTP hardware clock, I call it physical hardware clock, and that's like a more general term because let's say you have a PHC also on the time card, so it's not necessarily related to specifically PTP. It can do anything else, so that's why I want to call it again physical hardware clock. And so you can have this physical hardware clock again in sync, but then once you want to bring it in the application, it's a separate story. For telecom, this really worked because you take that PPS signal and you give it to, let's say, to your radios, and you do all kinds of things with it, and timestamp things and so on. But if you want to bring in the application, you really have to enter, let's say, the user land, and then nothing better than having this synchronization basically on the CPU, where you can now combine this, let's say, with the instruction that they get executed on the CPU, and also perhaps we can have time-aware threads that they basically can come up like on specific times. So this all brings us the ability to now go for GPUs, and again, beyond NICs, you know, like have, like now we get to CPU, you can go to everywhere else in the system. They can go to, let's say, a USB 3.2 controller, and now you can timestamp, let's say, different peripherals, and by that you can, let's say, I don't know, look for all these, let's say, mass online games, or like, you know, platforms where you can like now timestamp the clicks of like the players, or you can timestamp when certain players see certain, like, let's say, rendered images and so on. And I mean, going back to, this is like inside the machine. Now, if you have this capability inside the machine, now if you want to have it, let's say, between machines, now we can correlate these events precisely. Like, for example, you have these logs that you get in different machines, and today, because, let's say, again, provided by NTP or even PTP, after you go with a sync to the clock real time, you will still have a hard time to associate, let's say, different timestamp that these logs have if you're looking for something that was done across the network. Let's say, for example, there is some machine learning or something, and then there's some coefficient that from somewhere you want to propagate how this went through, let's say, due to an error, how it propagated through the whole thing. It's just hypothetical. You will have a hard time associating these timestamps of logs from one machine to the other one in the absence of PTM. But in the presence of PTM, perhaps you can do that if you have the granularity and, let's say, again, window of uncertainty, all of these things to the point that you can have like differentiating basically between different steps as you go to a log. Also, this inter-machine telemetry, where you can compare now, let's say, in setups where you are going from parallel to serial, and you have to wait, let's say, for all machines to complete before you can proceed. You can check how bad things are, and I have a slide, I'll show that more. And then if you have, again, the telemetry, you can perhaps do some alignment or even calibration. And by that is like, you can reduce the tail latency. And this can happen like by either you actively change the workload, or you can introduce something which I like to call micro overclocking, where you can, like, let's say, slightly make the machines that are due to a lot of things, you know, slower, because like I think it's slower because, let's say, the clock speed, but it goes more, it goes like the cache, RAM, like whatever is like heterogeneity is basically what we deal with. Like homogeneity is just an approximation. Like you don't have two transistors that are really the same, because that's how nature works. And so then from that you derive, you don't have two CPUs that are similar. And then there's also the binning process, but the binning process, again, you have a class of, let's say, certain CPUs that they get sold as one thing, but again, they like they're not similar. And what better than something so precise that can show you the differences, and now you can do some like, you know, fine tweaking to make them work more similar. And then finally, you have like the application that they apply to a network, like basically a larger set of like between machines, where now the network itself is one entity, and you have all these different pieces that they work together. So one-way latency is one of those where now you make the network interaction deterministic. So now you can, it's basically you're bringing back some of the good things that you had in SONET. SONET was not all bad. Again, SONET had like some shortcomings where Ethernet was able to beat it, but SONET definitely had some good things, and you want to bring those back where you still have the Ethernet. And then now you have, when you have all of these things, you can, this is a term I like to always use, pseudo entanglement. You have basically these counters that are across all the machines that they're entangled in some sense, meaning like when you read value of one counter, it reflects what the other one is, and all of them are within the window of uncertainty, the precision that you have between them. Again, the statistical things that apply here, because the process of like the window of uncertainty is nothing but looking for the variance, and then you basically are looking for how much, let's say, tolerance you have. So you look at like how many sigmas you can you have to look for in terms of likelihood to get, let's say, I don't know, to whatever is given. And then within that, you have this entanglement within that range that the uncertainty is giving you. So next, basically this slide I always like to show, where different, let's say, levels of precision will enable us with different applications. As you see, like industry standard, again, with NTP for, let's say, P691 in million is like 20 millisecond. Again, it's also all statistical. And then this is for a system where the NTP server is in the network. Like if you have it across the, let's say, WAN, across the internet, this number is not realistic. And now, when you want to, let's say, do things, let's say, in terms of linearizability and so on, NTP really cannot help you in that range. And that's why this is where we have algorithms like, for example, commit and wait, where that wait is basically there to buffer for this clock uncertainty that you have. So now, if you introduce PTP, you all of a sudden have a jump, let's say, where you enable a lot of things, but PTP alone is not good enough. So let's say for a lot of applications, and even like when you look at the PTP range, there are things, let's say, like for example, in network telemetry, INT, I wrote there, or like, for example, where you want to have like that, the alignment of different, let's say, pipelines. All of those, they require you to go, let's say, I don't know, all these applications that require you to go, let's say, sub microsecond, they need to have some tie with, let's say, PTM in order to bring those, let's say, that precision all the way to the user land. Otherwise, you are at the mercy of writing an algorithm that relies on the packet exchange, so you can do the timing on when a packet comes in or goes out from the NIC, rather than like processing things at the user land. And again, if you need to go further, then comes White Rabbit, and with that, basically, you have, again, PTM. Again, it's a must then. Otherwise, why you get so much precision and then you waste it at further? And again, this is an illustration of the correlating events between machines, where you see, like, for example, event 1238 on machine A can be related to event, let's say, 1405 on machine B, and like, I don't know, and so on and so forth, because you have the timestamps coming from the same reference, and you preserve the precision as you go through the whole system, rather than you just keep it at the NIC. So next, this is what I was talking about, let's say, for the parallel pipelines, where again, the inherent heterogeneity that is between machines that are like nominally considered, let's say, homogeneous, will reflect one way of like all these machines. Let's say machine D in this case does the job very fast, but because of machine C, it has to keep waiting until like things basically unravel. So next. So basically, this is the waste basically where we're thinking about to, let's say, resolve. And this varies. Actually, this is, let's say, varies if you want to with just consider CPUs or GPUs. What we notice is in GPUs, this number is definitely much larger. And in general, even with CPUs, this number is considerable because, again, it's not only the CPU, it's the CPU, how the RAM gets basically trained, a lot of things, cache, like, so the whole performance of the system relies on, like, again, a lot of, let's say, contributing factors, and there's nothing better than measuring all of that so you can compensate for it. So next is, that's what you hope to get. You align basically everything else. And there again, some more applications where I didn't make slides for it, but like, let's say, for example, if you want to have some sort of security on and being like, let's say, capable to avoid, let's say, a memory dump attack on a machine that you have physical access to, you can have everything expiring in much shorter times. Okay, so let's go hand it back to Lasse. We'll continue with the agenda. Who is the next speaker, Lasse?
So the next speaker is Kevin.
Awesome.
Kevin Stenson at Intel, and I don't have Kevin fire to hand. Do you?
Yeah, I have. So okay, so Kevin Stanton is a senior principal engineer. Kevin at Intel, where he is responsible broadly for timekeeping and time synchronization across the company, from CPU to software, Ethernet to I/O. Given that he was driving PTM before it existed as such, Kevin can explain the full history and why certain architectural decisions were made. Well, we in OCP TAP unofficially consider Kevin the father of PTM. So Kevin, with no further ado, the floor is yours.
Thanks, guys. Ahmed, I lost my right to share my screen.
You got it back.
Grant that. Okay, very good. Thank you. I will share this screen. Okay, thanks. Thanks, everybody. It's white for a second, but I'll make it non-white in a second. Thanks for the introduction. Thanks for, it's great to see so many old friends. I actually started in this area more than half of my career ago, and there are more and more people that are joining this timing community, especially over the last 5 years, I'd say. So it's really exciting to see that grow and make new friends. I'll also like to acknowledge a guy named Tony Bach, who was on my team at the time, who held the pen for the PTM spec at the time when it was written. So credit to Tony for actually creating the text that became the specification for PTM that was then implemented various places. So, all right, so timing in the last few centimeters. Ahmed talked about some hypothetical use cases, and obviously some of those use cases are real already. I like to think about it in terms of where time synchronization is important, and also where deadlines must be met. And there are a lot of applications, from embedded cyber-physical systems, audio, video, AR, etc., where time synchronization is a foundational piece of these applications. And then on top of that, and in some cases related to the time synchronization, you can also, over the network and through the software, meet deadlines as well. And then you could argue that many other applications on the bottom also have timeliness or deadlines as a criteria for the correctness of the algorithm. But I think about them as the lower the latency, the better, as opposed to some other applications where if the latency is not below a certain threshold, then the algorithm is incorrect. But in all of these cases, to simplify. Time synchronization is foundational, and we'll talk about some more of those, and many have been recorded in the OCP TAP archive, which is available on the website. So I wanted to what you'll hear as well as is what you'll hear today is a number of different views on on PTM. And so what we'll try to do is build on what was said by the previous authors or the speakers, but with a little bit perhaps extra emphasis. So Lasse talked about that terrible jitter between the network interface and application software. And so what I wanted to show here is just an example of those last few centimeters, and what you can expect in practice when you measure the actual pulse per second offset using some logic analyzer, let's say. So the network interface has some time, which might be super accurate thanks to PTP and hardware timestamping in the hardware. The system, the application, can read a POSIX clock in Linux, let's say the clock get time, and find out what time it is in the CPU. But that's not very, it's not easy to see what is the ground truth. So what we're showing here is a methodology where a pulse per second comes out of the software, the compute complex, every second on the second, based on what application software, not even in the kernel, but user space software thinks the time is, and schedules an edge on the next second. And then the network interface can also be programmed to put out a pulse per second rising edge on the second. And if we're perfectly synchronized, those edges should match exactly. So what we do here is show an example using software method that Lasse described, and then a PTM method on the next slide. And again, application level user software is involved in the path here. For the PTM side, for the measurement, as Lasse said, is very tightly controlled within the kernel to make it as good as possible. But if you don't have PTM looking at the ground truth, software thinks that the offset is 0, but in reality, we show here as an example a 500 nanosecond offset between the NIC and what the software thinks the time is because of the asymmetries, again, Lasse mentioned. So that's point number one. There will be an offset because you can't measure, you don't know where within that measurement of reading the CPU time, and in between reading the PHC time, you don't know exactly where that happens. So there will be some kind of offset if you don't have PTM. What's even worse is that if you have a loaded system with compute load, IO load, there's jitter. You would expect that because you're using software to try to make a measurement from a far away counter in the NIC. But what's worse is that the average increases. In this case, increases to beyond 1 microsecond. So there's no averaging that can eliminate that. And then with PTM, maybe it's not so visible here. So we zoomed in. We show very, very small peak-to-peak error, which importantly is independent of system load, or largely independent of system load. You could maybe say that it's off by a few nanoseconds or something. You'll see some more measurements in a few minutes from Wojtek, and he'll show some values that are slightly larger. Our methodology was slightly different, where we used the residue post-processing to come up with these numbers. But in any case, it's an impressive improvement over what you would see without PTM. So let's take a look at what actually happens when the application asks for what time is it. So in the CPU, there is there's a counter in x86. It's the read TSC RDTSC instruction, And it gives you a value of the timestamp counter, which runs at the max non-turbo frequency and is monotonic these days. There were times in the past when it was not, but these days it is. So what happens is this instruction is executed, which returns a value, number of ticks basically since reset. It's multiplied, shifted to give you nanoseconds, nominal nanoseconds, and that's what you get if you ask for clock monotonic raw, which is not synchronized to anything. And if the crystal changes frequency slightly because of temperature, that will vary, but that's okay. That's just the TSC in nanoseconds. If you ask for clock monotonic, now you have something that has been disciplined by this M, as in MX plus C, this M, which is adjusted by the kernel regularly in order to try to keep the value you get with 2, which is the clock monotonic, synchronized in frequency. So 1 second is 1 second with respect to whatever reference you have out there, GPS, PTP-GM, or whatever it is. And then if you ask for clock real time, it adds a constant, which typically is not going to change, ignoring leap seconds and that kind of thing. Question is, how do you get M? Where does M come from? Well, to calculate the M, you need to know the difference between this value here and your reference out there, which is perhaps present on the Ethernet controller, and either using software or using PCIe PTM, you capture these two values as close to simultaneous as possible. And really the benefit of PTM is that it's done in hardware independent of software and can give you a super accurate cross timestamp. The Linux PTP infrastructure has this ioctl, which is giving you this offset. And if PTM is supported in the hardware, both the root port and the NIC, then it automatically uses the _precise version of this ioctl. And instead of software trying to do the measurement, PTM is used to do the measurements. And so it happens automatically. It's all part of Linux PTP and the Linux kernel today. All right, I don't think we're not going to go in detail into the actual PTM protocol, but it's basically a two-way protocol over each link with 4 timestamps. From those timestamps, you can calculate the time offset. You can calculate the link delay, including any phi delay that's incorporated in the link delay. And so that happens on request, typically from the NIC. If there's a switch, the switch forwards it up. And the thing that you can do then is correlate, yes, the NIC PHC to a system time, but also a system time to another device. And therefore, through A to B, B to C, you can also correlate an A to C. And the idea is then you could even create a 1588 boundary clock or transparent clock or what have you, using the extra precise and accurate cross timestamp that PTM affords. Okay, I did want to talk a little bit more about that in terms of the switches. So the way it works is that, as I mentioned, the endpoint. This is a diagram from one of the early versions of the spec. The endpoint can make a PTM request, and it might get a response that says there's no data, but eventually the switch will also make a request up to the root port, which will provide a value back down through the protocol we just saw on the previous slide. And when it responds to the endpoint, which continues saying, hey, I'm asking for the time, I'm asking for the time, when the switch finally has received the time, if it doesn't already have a copy, it completes the transaction, but adds in any delay that happened over the link and any delay that happened in the queuing here between the north and the south end of the switch. Very similar to the way IEEE 1588 works if you have on-path support, if you have Ethernet switches, routers that include the correction field. In PTP, in PTP, it's optional to have that support in this Ethernet switches. In PTM, it is required to have the support in the PCIe switches, because we want to be able to know for sure what is the overall accuracy that we get. Okay, that was all I had, plus a disclaimer here, but that's all I have for my talk. I'll turn it back to our moderators.
Wonderful. Okay, so next we will go for Wojtek from NVIDIA. So Wojtek, let me see if permission works. I'll introduce Wojtek while Wojtek is preparing the slides. So Wojtek is a hardware architect at NVIDIA, where it tackles challenges of networking distributed systems, especially in the aspect of time synchronization. Wojtek often describes himself as a hardcore full stack developer, where the stack in question stretches from silicon architecture through firmware, driver, libraries, all the way to user-facing applications. So also, again, after we have like all the presentations, it will, again, we have after Wojtek basically another presenter, Brian Wheeler, and then we'll have basically a session for like basically we'll have some time for questions. So it will definitely be more than an hour. So bear with us if you can, and if not, again, it's recorded. You can watch things later. Okay, Wojtek, with no further ado, floor is yours.
Right, thank you. I'll try not to repeat the same concepts that were already mentioned, but I'm looking at how PTM works with the peripheral devices from the device side. What does it take to implement PTM on the device side, and why you want to do it, right? The reason we start looking into that is synchronization comes from the periphery, from the outside anyway. You have some external reference that you're getting into the platform, and there are multiple ways you can do that. And it was enough for a long time to just consume the synchronization signal at this periphery. And you always had some way to coarsely synchronize the CPU and other peripheral devices, but the precise synchronization outside of the networking adapter was a domain of very specialized and purpose-built systems. The early use cases for synchronization in commodity platforms were also networking oriented, things like time-sensitive networking, 5G front hauling. And so all this stuff could be offloaded to the networking device, which already had the synchronization. So you were consuming the synchronization in the same device that was receiving it from the outside external reference. But as my previous speakers mentioned already, there are new applications and new requirements that are coming in with demands for CPU and other peripheral devices that are not networking related to have precise synchronization. I'll make a quick segue to time uncertainty and how it filters into that, because until recently, we never really had a way to inspect the time on the CPU and how it relates to the time as perceived on the NIC, right? So the applications nowadays require a measurement, an estimate of local clock uncertainty. It's okay, often, it's okay if you are not synchronized down to double-digit nanoseconds, but you need to be able to estimate your local time error. And we never had a way to be sure about the time on x86, which was quite problematic for those APIs. We could try to assume the worst case in estimating this window of uncertainty, but the problem was, how do we estimate the worst case? And so we made similar tests to what Lasse was showing, but we didn't spend the money on oscilloscopes/spectroscopes. We just chained the PPS signals of two NICs together, synchronizing them through a CPU in the middle, and then monitored the PPS events at one of the NICs. And with that method, we measured hundreds of nanoseconds of time error that was introduced by this whole chain. And we suspected some sort of a smoothing effect of the CPU in the middle, where you have the inertia of the synchronization loop both between NIC number 1 and the CPU, and from the CPU to the NIC number 2. And why that is, previous speakers have already explained how synchronization between CPU and device works already. But just as a refresher, that you'll have some sort of an agent. In Linux, it's the Linux kernel on behalf of the user space application that queries the system clock, the CPU clock, the device clock, and then the CPU clock again. And it will do it multiple times and then apply some heuristics to try to come up with the best measurement for you to use, right? The problem is this picture is not as beautiful as I drew it right now. It looks something more like this, where querying the clock of the device, the peripheral device, takes much longer, which in of itself is not a problem, but there is asymmetry involved in getting to the device, asking it for the time, and for the response to travel back to the kernel space. And there's a high degree of asymmetry involved. There are queuing delays, ordering delays, arbitration delays, everything you can think of that can happen over the PCIe bus that will affect those measurements. So with the recent advancements in the x86 architecture, we now have the possibility of measuring the time with hardware signals, like Kevin explained, with the PPS output that is driven by the system clock, by the TSC that is driving the system clock. So we built kind of a test platform like this, where we have a Sapphire Rapids-based server with a Connectix 7 board, the 2 ports of the Connectix 7 of the NIC connected in a loopback with a cable, the PPS out from the NIC routed to one channel of the oscilloscope, the CPU clock synchronized from the Connectix 7 clock through PHC-to-sys, and then the PPS from the CPU routed onto another channel on the oscilloscope, where we can measure the time difference between the edges of those 2 channels. And like Kevin mentioned already, our methodology differed slightly from what Kevin and his team did. We just took raw measurements of the PPS signals. We did not do any post-processing of the results. So as I understand, the TGPIO on the CPU side runs off a relatively slow clock. There was a jitter that we expected and we observed in the order of tens of nanoseconds on this, simply due to the generation of the PPS being done with a relatively slow clock. And just to add a little bit of spice to this whole setup, we tried to load the system somewhat. It's nothing special, nothing dynamic. We just put a relatively static load of iPerf client and server between the 2 ports of the NIC, which resulted in roughly 120 gigabits per second sustained between the 2 ports, and obviously across the PCIe as well. And so we first run it without PTM, and those are the results I got for an 11-hour run, where I left it running overnight. In this test, I adjust the PHC-to-sys, adjust the CPU time to match the NIC time 8 times per second. And for this heuristic that we described, for each measurement, for each adjustment, we query the CPU NIC time combo 15 times in a row, and then use the luckiest measurement of those 15. And even with this heuristic in place, we could see that when the system was loaded, the CPU NIC time error was peak to peak almost 2.5 microseconds. And I think quite importantly, we did see this value grow larger and larger even a couple of hours into the test. So I don't know what would happen if I let it running for a couple of weeks. I don't know what the maximum value would be, but we definitely saw this creeping larger and larger. But we're here to talk about PTM, so let's talk about PTM. PTM is a simple spec, a simple feature in PCIe. It was designed to be simple so that it can be implemented without much fuss on the device, on the devices involved. It uses special PCIe messages which are not subject to the same ordering rules that all the PCIe reads and writes will be subject to. It requires hardware timestamping of the messages, those special messages as they come into the device and go out of the device. And it's based on the concept of distributing what is called a PTM master time, and it's expressed in nanoseconds. This PTM master time doesn't necessarily have to be this external reference wall clock time that you would synchronize to. It's more of a ruler by which every device in the system can measure the passage of the time according to its local clock. And then you establish the actual synchronization hierarchy on top of that. You have the measurements done through PTM, and then you can synchronize the CPU clock from the NIC clock, or vice versa, or whatever you need to do. You just have a common ruler through which you can measure the passage of time on all the devices. We've had it, NVIDIA ConnectX, previously Mellanox ConnectX, has had it for some time now. We have not enabled it yet in production software. There were no platforms to enable it on. But now with Sapphire Rapids, with the server platforms supporting PTM, we could do an implementation and test how it works. And so before I show the results with PTM in place, let's quickly recap what it takes to implement PTM on the device side, which is what we were looking at. You need some sort of a counter on the device, a counter. If you can adjust it on the device, that's really great. But at bottom line, you need the counter. Then you need the capability for your hardware to send PCIe messages with those configurable opcodes that are defined in the PCIe specification for PTM. Then your hardware logic in the PCIe needs to recognize those special opcodes and snapshot the counter that we mentioned previously when those messages are sent or received, right? And there is a little bit of parsing involved on the critical path. So in PCIe Gen 6 and later in the FLIT mode, it's even simpler to have a special bit that you can match in the FLIT and know that you have to snapshot the clock before even you parse the message and understand that it's a PTM message and not something else. But there is a little bit of logic required here, but you only really need to snapshot the counter when those messages come in or go out of your device. And then you need some way of communicating this information that you captured, those PTM messages, responses that you captured, and those timestamps that you captured to the host driver. And you also need to expose a capability register to tell the PCIe subsystem that, hey, I support PTM, so if you enable that, I will happily send PTM messages and do all the snapshotting and all this work. So it's relatively small feature to implement. And just to illustrate, my entire implementation for the PTM proof of concept I did was roughly 300 lines of code for multiple generations of our cards, including the documentation and the interfaces to talk with the kernel driver. So it's really a small feature to implement in peripheral devices. And for the last thing, let's show the results of synchronization with PTM in place, where I still synchronize the CPU time 8 times per second. But for each adjustment, I only queried the CPU NIC time once and not 15 times like previously. And you can see that under the same load, iPerf load of 120 gigabits per second between the two ports, we see peak-to-peak time error between the CPU and the NIC of 64 nanoseconds. Now, bear in mind, there is this jitter on the CPU PPS output. So this is probably as good as we're going to get. There is some small things that we can investigate and debug. But the performance difference in synchronization quality is tremendous. And most importantly, because those numbers are so low and are so stable, that means that if your system supports PTM, now your APIs that estimate the local clock uncertainty, the window of uncertainty, can return, do not have to artificially inflate the window of uncertainty due to the unknown time synchronization error between the CPU and the peripheral device. And I have a last slide that I think are a couple of open things in the PTM support, especially in Linux kernel. I think 2 points need to be addressed. I don't know how to solve them yet, but there are talking points that I think should be discussed sooner than later. The device driver is asked to cross timestamp its counter with the system clock. And there is no explicit notion of PTM master time in Linux kernel. So you kind of assume you're doing the cross timestamping between clock real time and clock monotonic and the device clock, like Kevin showed. But that really assumes that your PTM master time has a strict relationship with the system clock. And so you assume that some sort of in case of x86 Intel, ART, the always running timer, derivative is used for the PTM master time that is distributed across the PCIe hierarchy. And that the clock real time is based on TSC, which it doesn't have to be. And that the TSC is related to the counter that is used for the PTM master time distribution. So there are a lot of hidden assumptions in that I think need to be carefully examined and looked at. And further, the Linux API that we have today, the PTP sys offset precise, only really allows cross timestamping of the device clock and of the system clock. And while typically you would have a PCIe switch operating like what you would call a transparent clock, what Kevin showed, where you have the switch issuing requests based on the request from the downstream, you could have the PCIe switch maintain the local context and maintain its own local version of the time to serve the downstream devices. And there is no abstraction to express this in Linux kernel. So maybe Linux kernel needs some sort of a notion of PTM master time and the ability to express that the PTM master time is in some known constant relationship with the clock real time. I don't know what the real solution to that problem is, but I think there is some small amount of work that still needs to be done for the software on PTM. That's
Wonderful.
it.
Thank you. So in the interest of time, we'll go quickly to the next presenter, but if you can stay around for the question session, that will be great. If you have to leave, feel free, put your question in the chat box, and then we'll go through the questions, and then you can watch later the answer basically recorded. So Brian Wheeler, technical marketing engineer at AMI with over 15 years of experience in foundational technology industry. He grew his skills and expertise in boot firmware development and technical training. Brian currently focuses on creating and enhancing customer engagement across all AMI products. So basically, if you're sold on this like technology, you want to have it and so on, there is a blocker right now, and that is, I mean, PTM is enabled luckily on all the BIOS, whatever like motherboards you have, if it's Gen 11 plus on the consumer side from Intel and the latest Xeon. But PTM comes also with TGPIO, which allows you to basically send this pulse from the CPU to look at things. That one is not by default enabled. So with no further ado, let's give the floor to Brian, see what's the latest.
Can everyone hear me now?
Yes.
Okay. So hello, my name is Brian. I'm a technical marketing engineer here at AMI, and I just want to start off by just saying AMI is very enthusiastic about working with OCP and with Intel, NVIDIA, and TimeBeat. Our collaboration with TAP is like basically it's allowed us to get a deeper understanding of the importance of PTM and firmware's role in PTM enablement. So we're proud to be the market leaders in supporting PTM throughout boot firmware. And let me see if I can get the slides working. So for those that don't know, AMI, we are a We are a provider of platform firmware. We're the world's largest provider with about 80% of the server market and about server market, and about 40% of the client market. So we're uniquely positioned in the center of the compute ecosystem. So for enabling silicon and for customizing firmware for our partners and our customers. So as he kind of alluded to already, AMI's experience is in enabling silicon and features with firmware. Currently, we provide boot management and security solutions, and in nature of OCP, we do have some open source editions available for each of those that are available now or actively in development. So a little bit of the story, or a little bit of the background here, is that our interaction with TAP started in about 2022 when Ahmad reached out to us with the goal of raising awareness for PTM and using the enablement of TGPIO and on NUC platforms as the vehicle for that. So for those that don't know, TGPIO stands for Time Aware General Purpose IO, and TGPIO is a Intel hardware feature for precise time synchronization through GPIO pins controlled using timestamps. So this feature's been available, as Ahmad just recently said, around the Tiger Lake, been available since around Tiger Lake time frame, but it's just not enabled by firmware on all boards. So simply put, most of your off-the-shelf boards probably don't have the silicon feature enabled by firmware. So at AMI, our senior director, Stephen Vigneault, and our senior engineer, Michael Diedrich, coordinated with the Ahmad's team, and we coordinated with the team to provide BIOS images that enable TGPIO. So for us, TAP sent over several Intel NUCs, and we flashed them, updated them, and we provided a way for them to enable TGPIO in setup, using the switch in setup. So what you're going to see in this slide here, when you take a look at it, is that it's just highlighting the needs, the challenges, and the solutions about PTM, and showing how they are centered around awareness. We can't make all the changes necessary here overnight, but with awareness, we can start moving the needle. The industry, as we can tell, needs precision time synchronization. And with several vendors in the market, the challenge is getting a common solution for the industry at large, especially for enterprise and hyperscalers. Right now, AMI is prepared to enable this feature of TGPIO for all the supported platforms. So, as I think Kevin already brought this up, why is PTM important? Here's a couple of sectors that we see benefiting from PTM. 5G networks. The rise of 5G means more data, more devices that need this optimal communication. And so simply or essentially said, the more data, the more time synchronization is needed. High frequency trading. Speed is at the heart of high frequency trading, and nanoseconds are critical to the bottom line. So trades need to be processed with minimum delay. And then you have the automotive autonomy. Cars are becoming smarter, they're becoming more connected. And so as our data collection happens more at the edge, we need the time synchronization. Well, time synchronization becomes more important because decisions are made at the edge as well as at the core. So for AMI, we're proud to be market leaders in this area of PTM. We're happy to be working with TAP and TimeBeat and just being able to enable this just so everybody can see demonstrations of how important this is. We do believe in the work, and we want to ensure that PTM is enabled by default. And so AMI is committed to working to get TGPIO available in our open edition version by OCP Global in October 2023. And that's all I have for now. So I want to say thank you for everybody for listening. Thank you to Ahmad and Lassie for reaching out to us and inviting us here. And we're ready for any questions that you might have.
Thank you, Brian. So let's basically go for the question sessions. So I'll start with the first question here, mainly as an icebreaker, so we'll make the others a little bit shy. They can easily come to the questions. So the question is, where should PTM be placed in terms of standard? Would it fit, let's say, would this fit also part of the 1588?
Where does PTM fit in terms of a standard? So you're asking that, is it okay if I respond, Ahmad?
Yeah, go ahead.
All right.
Yeah, any one of the speakers, feel free. If you, I mean, the questions will be probably obvious where they direct.
All right. Yeah, thanks. Yeah, PTM is well specified. The PCI specs are owned by the PCI SIG, and PTM is a full function, fully supported, but optional feature of the PCIe spec. So the standardization is, let's say, done, and it's just really about implementation and getting broad industry support for switches, for example. But it's a complement to 1588.
That being said, I would still argue that some more standardization of the performance that you can achieve with synchronization across PCIe might be useful. Like we have ITU-T standards for testing and measuring performance of telecom clocks. And what if you build a chain of clocks that involves not only PTP, SYNC-key, and other methods of the network distribution, but also PTM? We do not have standards that tell us how to test the performance and how to quantify it.
I agree, Wojtek. A way of measuring and reporting performance in a standard way would be an enhancement. I agree.
And the switch that you showed, that acts more like a boundary clock. Is there also a transparent clock version of it? But I think you will have a hard time with it, right?
It works like a transparent clock, not a boundary clock, and this is how it should be, I think.
Agreed. Yeah, it's more like a transparent clock.
I see. Okay.
Yes.
So the
Because
correct to pick it up, right? From this, right? Yeah. Okay.
But because the issue is, and Wojciech, you made this point that you think, okay, it should be a boundary clock, but it becomes unmanageable for the same reasons that boundary clocks are completely unmanageable. Then how can you know whether these different switches actually have the right time? I agree, when you're closer to the hardware, okay, determinism is easier, but why do you want the logic there, and why do you want to have, then you have to have algorithms synchronizing. They become dramatically more complicated. I think it's not a good idea for the same reasons that boundary clocks in general are a terrible idea. I want to ask you a question though. Okay, you said you did a test. Okay, you showed a lab where you had you were trying to measure essentially between the Connect X7. And by the way, I want to say it's very cool that in due course it will be supported from like the Connect X5 and upwards. But did you ever, and you had one where you used the TGPIO pin, okay, to test the quality of the synchronization between the NIC and the CPU. Did you ever do a test where you had two Connect X7 and then you said, yes, but in fact, we saw like a variance in the tens of nanosecond range because okay, of the low frequency of the clock. But did you ever try between two Connect X7s via the CPU? Because you should surely have the capability to do that as well. No, so do you know what I mean?
I'm not sure I follow. So you want a NIC, CPU NIC?
So I want two Connect X7s that are both generating a pulse, one which is free running, the other one which is synchronizing from the CPU, which is synchronizing from the first one, but both generating a pulse. Did you ever try this?
But using PTM for the synchronization, I presume.
With PTM, yeah.
No, I have not done this yet.
Do you mind doing? Okay, can you do that and tell me how it goes?
Yeah, sure. I mean, I'll add it to the list of things we have to do for productization, right? I mean, we've done a proof of concept, we've done some exploration and some measurements, but now it's the hard work begins of how do we characterize the performance and make sure that it's always at this kind of level. And those tests that you're describing will be part of it.
Yeah. Okay, cool.
So we have a question from Nobu about, is PTM a complete work in terms of protocol?
Did it complete work? Is that what you said, Aman?
Yeah.
I guess I don't understand. Maybe I don't understand.
Nobu Lou, do you want to elaborate on your question?
Yeah, so actually Kevin already answered my question already, but I mean, is it going to be changed in near future, or it's already sort of set protocol?
Yeah, it's a good question. I think it is true that all successful standards do evolve over time, but typically give some backward compatibility. There's been a couple of updates to the PTM spec over the generations of the PCI standard. But yeah, it's a complete, it's ready, it's implemented. As you saw, people are using it.
Okay, thank you.
So next question is by Bob. Is there any variation to PTM with PCIe versions, for example, Gen 5 to Gen 6? And are there monitoring tools supporting PTM, such as like from Teledyne LaCroix or Serial-Tech, or I'd also, let's say, Calnex? So let's start, probably the first part of it, again, goes back to Kevin.
Yeah, I think in practice, I think it's a great next step, unless someone has a more detailed description of that. But in theory, so long as you're fundamentally you're limited to wherever your clock, your time stamping in the PTM logic with these TLPs going across the link, your accuracy, like PTP, is going to be limited by the accuracy of that and the asymmetries. And transmit receive on both sides. So in that sense, there shouldn't be any fundamental necessary limitation between various generations. But in practice, it's an interesting thing to measure.
Yeah. So quickly also to reflect on what, let's see, I think my share screen probably will not work because it needs a update. So yeah, let's skip that one. I was going to show you basically the test that we did with the NUC 11 from like what the BIOS change we had, like was a NUC 11 TNH, which you have a built-in I225 and then one that sits on a M.2. And then we had PPS output from both of them. And one of them was with a TCXO and one was just a crystal oscillator. And then there was another one that had the same thing, but the CPU was also a TCXO. And then I did a comparison between the two. What I didn't do is basically what Lasse is asking, where one of them goes with PTM, one doesn't. And main reason why I didn't do it is because off the shelf, PHC2Sys, the moment it recognizes as PTM, it will go on PTM. And I couldn't, let's say, switch it off for one of them while the other one not. Either I had it enabled or not, but I tested with and without on separate sessions, and where I saw like that 500 nanosecond offset, and then when you put basically more workload, it jumps on and off. Anyways, so next.
And Ahmed, another part of Bob's question, hi Bob, is related to test equipment. And again, I think that would be a great topic for OCP TAP to take up. Along with what Wojciech was saying with measurement methodologies. I think that would be a great next step.
Anyone from Calnex or Teledyne or Serial-Tech or any other measurement provider wants to speak on that?
Yeah, go ahead. I know that there are analyzers, but I don't want to try to list them out and be incomplete.
All these NDAs, right? Okay, so hearing none, let's go next question from Yang Kim. Does CXL.io also include the optional PCIe PTM? That's a great question, because I always wondered like what happens with the CXL. So anyone can shed light on that. I guess also falls on you, Kevin, right?
I'd be happy for someone to chime in first.
Sure.
Okay, because the reason I said that is I'm not prepared to talk about that. I don't know. I'm not prepared to have I don't have an answer for that. So yeah, we could perhaps follow up on that.
And I think it has also a follow-up. And if so, the UCIe, D2D, CXL, and I mean CXL is really very attractive. Like if you can, I mean you're very close to the CPU, Now, like you have all these different, let's say, peripherals, just for the lack of right terms, let's say in terms of storage and everything, like you have this non-volatile or volatile, like it would be really great if you have PTM right there, because now you can have the linearizability per se on what is stored on the CXL. So, okay, so I guess you cannot add more to that, right, Kevin?
Not today.
Okay, not today. Great. So next one is from Benoit. Did you characterize accuracy of PTM in case there is a lot of clock adjustments on the NIC card? So that goes to Wojtek, I guess.
So in my experiments, the NIC was completely free running. Just to isolate the performance of PTM, I probably would have fed the NIC with an external clock source that was extremely stable. I did not have that option at that lab, unfortunately.
Nice.
The concept of adjusting the NIC clock multiple times and very often from an external reference is something that should be tested. Again, going back to this concept of how to build clock chains that include both PTP and PTM on the path. I did not test that. I would not expect this to have a significant performance, as the clock tree within the network adapters is typically largely unaffected by the adjustments that are done to a central location, and then the signal is distributed to all the timestampers within the hardware.
I'll just add that when you adjust the clock, then of course you're cascading PI controllers, for example, which can end up with you can introduce second order effects. So I think it's a great question and something to keep in mind at the system level.
Just let me just add one remark, because if I understand your presentation, the master clock is you mentioned that the master clock should be the root clock, no? And all the adjustments should be made again this clock.
Right. Yeah, that's right. The requests for PTM always go northbound in my diagram from the device, perhaps through switches to the root port, and the responses always come down. And like Wojtek said, it's just a ruler. The PTM master clock is just a ruler that you use to line other things up. So you don't need to use, that ruler doesn't need to come from any specific device. You just have to choose one. And for PTM, we chose the root port as the thing that will have the ruler, that will specify the one ruler.
Okay, thanks.
So
by the way, do we go through the list or we can chime in?
Yeah, I'm going to
prefer
quickly through the list. I hope I can exhaust the list and then we just open it. Is that good with everyone? Okay. So
That's
next
okay.
one. Yeah. Next one. Do you have a question? You can go ahead.
Yeah, because I was curious about the performance penalty of using PTM, like, how many PCI bandwidth does it cost when you enable it and use it, and how scalable can PTM be? So, how often can you do those operations of getting the gross timestamps?
I'll speak up.
It's all on you, Kevin.
So the rate, the rate is determined by the period, the amount of frequency change that could happen at steady state. How much frequency, how many ppm per second will your reference clocks change in your NIC, in your CPU, in the GM if it's moving. And that's the default. The rule of thumb is usually a handful of those per second. So let's say 8 or 10 or 20 per second measurements per second. So that would correspond to a few tens, less than 100 PTM messages per second over a PCI bus. That is, they're relatively fast these days. So in terms of bandwidth on the PCI link, it's very negligible.
So Lasse, Sorry, go
My
ahead.
question is a bit different. Like, how much can we scale it up? I mean, how many clients of PTM, for example, can we have simultaneously? Or if you have a single NIC that has, hundreds or thousands of virtual functions, if every function starts to
Yeah.
try to issue PTM operation, what will happen? Is it scalable to that level, or
Yeah.
no one tested it, or it's not?
Yeah, it's a fair question, and I'm glad you mentioned virtual functions. That probably could be a future session as well, just talking about how time and virtualization relate to each other and how you keep from how you avoid destroying the time when you go from one VM to the other. But I don't have a specific answer to that. It really will depend on the specific platform. And maybe we have a follow-on discussion talking more about that in terms of the metrics as well.
Wonderful. So quickly, Lasse, can you show the slides, because I wanted to show everyone. So what we did, this was presented in WSTS. So basically, let's go next slide quickly. I don't want to make a presentation, just want to show basically the results. So here was, like I was making this point that if you go for PTM and you're designing like an SMB or something, it's good probably also to invest on a TCXO, because you can see the results directly here. So next slide. Like basically the work was done based on again, TCXOs, the prices is coming down with the technology, and you can get somewhere from $3 even, like a TCXO, all the way to like higher up. And then next slide. And so basically we did the test of all permutations: CPU, normal CPU, normal NIC, CPU TCXO, normal like NIC, normal CPU oscillator with a NIC with a TCXO, both side TCXO. And the result, let's go next slide, was so again, we used a time tagger to basically check the 4 combinations. Next slide. And again, thanks to SciTime for providing us the oscillator. You see, I dead bugged it here for the CPU. And I basically just took the crystal off, and then I put it to one of the inputs, TCXO. And the hardest part was actually finding a stable 3.3 volts to power up the, you can see it right beside the coin cell battery on the left bottom screw, the retainer of the CPU. Next slide. And similarly, I had to do it on the I225. So for the CPU on the TNH was 38.4 megahertz, and on the NIC was at 25 megahertz. So next slide. And here are the results. So with like just changing one of them, you see like on the graphs, you get better precision. Changing both of them, you get dramatic like precision. And again, the cool thing is like there's no long tail. Like you basically have 0 after like, I don't know, I did like 2-3 days running it. You really have nothing coming out of like that, the range, like I think it's plus minus 30 nanosecond. Again, this was not using something fancy like Lucky Packet where TimeBeat provides or something. This was simply just a PHC2sys, and it was giving us a lot of things. Thank you, Lasse, for sharing the slides. So next question is by Marek, which basically is asking about the standardized test. I'm assuming like probably, again, I can answer that, but it will hand it also to Kevin, is like TGPIO is how we can test things. You put on the scope, if I'm understanding the question right. Kevin, you want to elaborate anything more on that?
No, I think that's right. You can of course see much lower jitter,
yeah.
But with a very stable oscillator, even if they're not OCXOs, they're just standard XOs, but you don't have temperature variation. Yeah, software will eventually close the loop and believe that the error is very small on an idle system. But yeah, to get the ground truth, you really want to see a pulse per second hardware pulse out of it.
And again, I think, I mean, hopefully we'll have from one of these vendors of measurement devices, let's say, again, wish list, right? A device that you basically stick in a PCIe card and it can track what things are going back and forth, and it gives you some performance indication or something. I don't know, like, can be useful, I'm assuming. But if you have TGPIO, an oscilloscope would be sufficient, because I mean, you can have something a little bit fancier that shows you, like the time tagger, which shows you, like, let's say, correlation and histogram and things like that. But it really depends how deep you want to go in. So next question is by Thomas, which is, does the host side handle PTM if the PCIe device is identified as Gen 2 device, which includes correct PTM messages?
Yeah, from a spec perspective, PTM is not tied to any particular gen, and I wouldn't be able to say with certainty that all of the gens, if you plug in a Gen 1 or a Gen 2, someone else asked the question of what is the accuracy implication. I don't have that data today, but there's nothing that should limit the ability of an implementation to support all of the generations of PCIe.
So next question is by Nobu, which is asking, is this data basically based on a TCXO or an EXO? So I can, like, with confidence say on the CPU side, it's an EXO, it's not a TCXO. But again, I tested with the TCXO and you see dramatic improvement. On the NIC side, I'll leave it to Wojtek. So Wojtek, is it a TCXO or a EXO?
That Connect 7 was TCXO based.
Wonderful, and that explains why you had like a tighter, let's say, precision than, let's say, the i225, which uses a regular XO. So very interesting. So next question is by Hisham, which is asking me to elaborate on using time synchronization for telemetry using multiple pipelines. So basically, the telemetry for multiple type pipeline, what I meant by that is you have the runtime on different pipelines, and you can either, again, depending on the application, you can reduce, let's say if it's like machine learning or something, you can reduce, let's say, the batch sizes, which that comes with some unknown implications, or if possible, you can, let's say, overclock those that are slower to reduce the variance between the machines, so you have less machines, waiting for the slow ones, because you're dictated in that session to wait for the slowest. Hisham, is that answering your question?
Yeah, what is this? Yeah, this is good. So the like in test and data center, you would like to synchronize the outcome of all those machine learning devices.
Machine learning can be, like, basically it applies to wherever you go from a parallel pipeline to a serial, where you have to wait for the completion of everyone.
Got it. Yes, good boy. Thank you.
You are. Okay, so we exhausted the questions that were in the chat. Now we open to more questions from the audience. Don't forget to unmute.
I'm going to break the ice. I was just wondering if there is, because we just talked about an application, and there is a nice test with PTM, but I don't think we have any kind of good proof of concept with a real application behind. And I believe that maybe it will be nice to say, okay, we should focus on this application where the CPU really needs time and do a proof of concept. And I think it will be great to really show the benefit of TTM, because now it's okay. We get a very precise PPS on the GPO, and that's all. We have no really something to show that okay, it's have a very good benefit to the applications. I don't know if you have already think about it, or it's something that's still need to be considered.
No, that's a great question, and from my side, this is work in progress, and we have a lot of conferences ahead of us. Like, also, it's a good segue as a reminder. We have about 4 weeks and a half until the deadline for submitting abstract to ISPCS, which this year it will be in London, in September in London, in NPL. Again, I'm trying my best with my team to get something that we can basically submit there. And if anyone else likes to collaborate and hardware is your problem, please let me know and we'll see what we can do to help you. After all, we're a community. We try to help each other to basically tackle these problems just for the sake of pushing the technology further. Kevin, do you want to add something? Is there application in mind waiting? Or...
Yeah, I'll just mention that where correctness of an algorithm is involved, often you need to know what is in the total end-to-end budget, you need to know what is the worst case time inaccuracy that you could actually observe in practice. And so that has to be characterized somehow. And as you saw from some of the data, it can be difficult to put an upper bound on that. And so you have to make some kind of number of nines of assessment of here's the worst case time inaccuracy in the last hop. And in some cases, insert delays because you're using up your, there's too much uncertainty. So reducing uncertainty and time accuracy, the time accuracy uncertainty, reducing that can actually remove inefficiencies in the overall system when you're talking about time coordinated distributed applications.
Lasse, is anything you want to add to this?
No, there's nothing I want to add to this. I want to say that I thought this was great, and when we first talked about it, I thought it would be interesting. This was great. I thought this was really good, and I mean, from our perspective, so we talked a lot about what are the applications, on the client side. For us at TimeBreed, okay, the interest, okay, yeah, for sure it's that, but for us it's also moving time distribution onto commodity servers where the scale of distribution can go up by like 3 or 4 orders of magnitude from what's possible today, right? So, so that's sort of where our interest is. Yeah, but I thought it was good.
Ludwig, you want to add something?
Yes, I've just one question. Where can I find the presentation?
Well, the presentations will be published on the wiki. So ocptap.com, and then you will go to the wiki, and then on the wiki you see this recorded video as well as all the slides.
Can you just post the website because
yes, if you scroll up in the okay. Chat, the first link.
Okay, I see. Yeah, I find. Okay.
And to everyone else,
good to see you.
Okay, good to see you, Kevin, as well. I'm retired now, but I'm still working on TSN. Okay.
So to everyone else that's new to this forum, again, we have this bi-weekly on the same time, basically 11 Pacific time. And if you have like a presentation you want to give that's related to time and like time dissemination, timekeeping, all these things you see the special interest group, basically feel free to reach out to me and then we schedule you. And again, you can see the schedule for upcoming talks as well. So let's see if there is any more question.
Yeah, I have one question. Are there any platforms available in the market with TGPIOs enabled? Is the work that you do with AMI somewhat accessible to others, or is it NDA only?
Yeah, let me, I'll give the first part of that, and I think Ahmed will have another part. If you search for TGPIO Intel, you'll see a number of pages that talk about specific products that are out in the market and fully supported with TGPIO. What Ahmed and AMI are talking about is an effort to make that more broadly available. Ahmed?
So we had a conversation with Intel and AMI And I don't know, like, again, probably I have to check on that again with AMI and Intel, because again, so there are two parts of this. So one is basically the enablement that AMI has to do, which it will be great if somehow we can get AMI to release a special BIOS with, let's say, I don't know, a bunch of disclaimers that if you use this, blah, blah, everything is on you for experimental purposes, whatever. And there is the part that now you need to do some hardware modification. I can tell you about everything that's in the market from the NUC perspective, which one, and maybe we can narrow down something that is relatively easy to hack, because I mean, at least you need some soldering skills, because you have to tap into a super tiny pad, bring it out, have a, I mean, you can bring it out and not worry, let's say, about reflection. But if you care about reflection, you want to have a nice slew rate, you need to add also a little board. I mean, I made these boards to basically take care of the buffering, and it's going to 50 ohms, so then you can have like a sharp edge going up. But other than that, I think this is something on me, Kevin, and Brian, like, I mean, AMI, and I mean the rest of the NUC team to let's say do something about it. But I kind of, Kevin, correct me if I'm wrong, I kind of got a promise from NUC's team that any product that comes out will have some easement for.
And I just say stay tuned. You know, we'll.
Yeah.
I will add this. The TGPIO feature was initially intended, was not, I didn't think that it would get so much interest, frankly. And so that's part of the history, was that it was intended for the platforms that we advertise support for it today. Yeah, stay tuned. There are discussions about what more can be done.
This is very interesting.
You can blame Ahmad for the interest.
Yes, no, we're showing you. This is the board basically, and I put this one also on the GitHub. So if anyone needs that, it gives you two PPS, like two SMA U.FL connectors that you can use either input or output, and you can, again, even on the CPU, you have two TGPIOs. I never got the input working, but apparently that's also possible, where you get a precise timestamp from the TSC or ART, and then you can do a lot of cool things. I don't know, GPS direct.
Yeah, but that will probably need some driver, right?
That's right. That's right. The driver, again, driver is also not openly released. That's another thing, Kevin, we probably need to work on. That repository is still private. So thank you, Nobu.
Yeah.
But meanwhile, again, you can reach out to me and we can figure out something. I give you something you can try it for now, at least. But if you want to just try, again, I want to make it very clear. If you want to just try PTM and let's say just look at the precision, not the accuracy, you simply buy a off-the-shelf Intel Gen 11, 12, 13, like just a simple NUC, and then make sure, again, the NIC is also, let's say, i225, which it is on those platforms. And you have PTM right away available there. Basically, use TGPIO. TGPIO notices PTM is enabled. If PTM is not, it doesn't work, you just probably need another kernel compile where you enable the flag for PTM. As simple as that, literally. You don't need anything else. And PTM will work. And I mean, you basically, after you boot, you check if in dmessage, if PTM was the dmessage, let's say grep, PTM. And if you see that it says like 4 nanosecond granularity, everything is good. So then you run the very old, like very familiar PHC2sys, and PHC2sys will act, again, thanks to Kevin and Chris Hall, which they have it already like mainlined. Tool is there, and you have PTM out of the box, and your clock underline real time automatically is precise. And if you have PTP to that NIC provided from, let's say, Grandmaster, whatever, time card, whatever, then you are like in sync. You can do everything you're looking for there but again, you have to trust that accuracy is preserved. If you don't trust that and you want to see the accuracy on the scope, which I always refer to PPSs or currency, then yeah, you have to go and you have to wait, or again, we figure out somehow we give you access to the TGPIO and then test it. Again, this TGPIO, as Kevin mentioned, was perhaps a tool for Intel internally to validate their work, but then because of the interest, now we are like, hey, we want to have access to it. This happened, the same thing happened also with these atomic clocks, where PPS in and PPS out was something that they were using for validating the clock, how things work. But we're like, hey, we have application for this. We want to have access to this to do, let's say, I don't know, or synchronization, and then like use this as a backup. So it's very interesting when something was just for test becomes interesting.
Yeah, and specifically for the use in industrial automation and those kinds of places. And again, if you search for TGPIO, you will see some official documentation. Ahmed's gone outside of the official set of platforms and done some creative work. And yeah, let's see what we can do.
Wonderful. Stephen, you want to add something?
Yeah, I just wanted to speak to that. You know, for people that are involved in OCP TAP that are wanting to you know, contribute to the different measurements and experiments and everything, we can look at the platforms that you can do that on, but the end goal that Ahmad and I had discussed months ago is to create, verify that this is a necessary item, and then drive awareness for it and get it to the production level. So here at AMI, we'll be taking some steps to talk to some of the companies that were interested in this and work that back through their ODM suppliers. Of course, this would be outside of, you know, any decisions made by OEM products like, you know, Intel in control of the NUC, which Kevin spoke about a few moments ago. You know, that's a product management decision on their side, but AMI stands ready to enable that. For companies like system integrators that are building servers that go into telco or into fintech or a number of different areas, many of those companies are already licensees of our system BIOS. So for those generations of Intel chipsets that support TGPIO, we can facilitate them immediately. Any of the pull-ups that Ahmad was talking about, that probably should be some sort of a reference design. If that's necessary in a production product, I don't know. We could probably have a sidebar conversation around that. But if we think about what that is, AMI has enabled this in our core. There's no additional you know, cost to the ODM. But they're always reluctant to retrofit a past design because you know, they don't want to introduce any support issues or anything of that nature. But when the demand starts coming from their customers, that's when they'll start paying more attention. And it's relatively simple to enable it on any of the new designs or refreshes of existing designs. So we still got some work to go. It's good to see the success that Ahmad and his team at TAP have accomplished to date. I know that some of the guys introduced me to some people over in Germany. I'll talk back to them. They use one of the Taiwan motherboard manufacturers for the heart of their server that goes into a financial data center, and see if we can encourage them to be a pilot for these types of activities. So the more those types of connections that we can make, AMI has a significant size team in our Taipei office. And if we hit 3 or 4 of the companies that are building servers on the more recent Intel chipsets, then we can, it'll pick up a momentum and then it'll just hockey stick. It should be a default feature, is what my opinion is. If it's enabled in the silicon, it should be a default feature.
Yeah, the problem is that we are currently in a chicken and egg situation where, you know, there are some efforts that could be done to enable more use cases of it, but there is no platform to validate the assumptions or, you know, do anything
Right.
more about that.
Yeah, so that's
you
the
know,
first
having
part of the equation, and that's what Ahmad and Julian, his team, and I worked out with Intel's consent to enable it. We declared it in the demo mode, which basically shields. See, an Intel product manager would have to make a decision about enabling it on a NUC. If we make a modification to it, sort of a hack, and declare it in a demo mode, not for, you know, commercial use or whatever, then we lift that burden off of them. We also violate the warranty on the NUC, but Ahmad was okay with that. and
yeah, this is fine. Like, you know,
so,
I'm
so we
looking
can
for
repeat that process with different other platforms out there for those that are continuing the work of TAP. But that will ultimately lead us to getting more awareness, and then we can drive that back by the consumers of the volume hardware to make this a de facto standard. And that may take another year or so.
One thing
Anyway.
I want to add for Machi is some of the platforms, let's say, for example, the Stu NUCs, it was not very hard because the pin was like, there was some other pin that was exposed there, and then you can basically just access it. Again, you still need some basic soldering skills. And some of them, it was next to impossible. I mean, I took the challenge where it was like, especially for those, again, if you look at Intel, there are some CPUs that the bridge, the PCH is built in, and some of them the PCH is separate. If the PCH is separate, you might have less luck because it's one of the, if like one or both of the pins. Again, this is all public knowledge because you can look at the pins and everything. So one of the pins, so both the pins that you want to get for PTM, they're buried in, they're not routed out. So for one of them, I had to literally drill a hole from one side of the PCB. And again, I have access to fine drills and X-ray, and I looked at like not hitting basically another trace as I'm going down. So the moment I expose it, I put a wire, and again, because of some NDA here, I cannot show it, but I got it work. But that was like literally the pinnacle of my soldering skills. Like, I don't want to recommend that to everyone. Like, that was crazy. Again, it was an extreme, Nick. Extreme.
Yeah, but also, you know, I also have some, you know, Chinese platforms that have some of the GPIOs on a header exposed, but I don't even, you know, I tried to look for some documentations which of them are required, but wasn't able to find necessary documentation. So maybe that will be a, you know, way around it.
Yeah, what I'd say, Ahmed, is I do think that there is a need for some working group, probably part of TAP, to have discussion about measurements, and also this doing the hacking, the tweaking is you know, that's fine, but I think we need to figure out how to you know, this will need scale in order to make a difference in the end of at the end of the day. So both of those are,
Yes,
I guess, valid valid directions, but I'd suggest that given that we're 50 minutes over at this point, I think maybe we take that up in a follow-on TAP subgroup. I don't think there's one that's currently actively talking about this, but it would, I think it'd be a good next step.
We certainly can do that. Can have a, sorry, go ahead.
Yeah, I just said okay.
Yeah,
works.
I mean, if you are interested,
I think a reference platform would be awesome, because then it would open the possibility to experiment for more people.
Yeah, how about we sign you up for that?
I'd be happy to join and do what I can.
Wonderful. And Machi, you as well?
Yeah, sure.
Yeah. So I will get back to you two, and then anyone else, and we can increase that. So Rodrigo, do you have a question?
Don't hear
Anyone else? We are 50 minutes beyond time. Again, another record Lasse broke. So 1 hour 45 was, I think, the last one. Now we're 1 hour 50. So
This is a great session, Ahmed, really.
yeah, I mean, it's credit all to Lasse. He really worked very hard on this. Any
Good.
more questions? Don't forget unmute. Okay, hearing none, once, twice, three. Okay, let's adjourn, and we'll see you in 2 weeks. And please, to the presenters, please send me the slides so I combine them in one. I can put them on the wiki. Wonderful. Okay.
And will you also be able to post the results that you talked about that you haven't shown?
Which one?
The ones that were comparing the performance of the TGPIOs with the TCXOs.
Oh, that one was mine. Yeah, sure, absolutely.
Awesome.
That was a poster I presented in WSTS.
Unfortunately, I missed this one last year. So
oh, no problem, no problem. I will include it all in one post, like PBTX, and I put it on the thing.
Mm-hmm.
Okay, great.
Great.
Well, enjoy the rest of your day, guys, and night, whatever time zone.
Thanks, everybody.
Okay.
Thank you.
Thanks, guys.
Thank you. Bye.
Bye.
Bye now.